Hello and welcome to another recreational programming session. So today is Friday, if I'm not mistaken, and that means today, according to the schedule, we're doing a random one-off topic, and that means I'm choosing the topic and I'm doing a session on that topic for one session, a single session for one topic. So the topic of today is going to be rather interesting. So I've got this interesting idea that I wanted to implement for quite some time. So let's actually go to C and allocate an array of bytes, right? So it's going to be array of characters, something like this. So how many bytes do we want to allocate? I think we want to allocate like 640 kilobytes, right? Because that should be enough for everyone. Might as well actually call it something like capacity. And just put it in here like this. So this is going to be capacity. So let's call this array a heap, right? So this is going to be our sort of heap. And let's implement two functions. Heap alloc, right? Which accepts the size of the chunk of the memory that you want to allocate, and this thing is going to allocate that chunk of the memory into the heap, right? And something like heap free, which will accept the pointer to the memory and is going to free the memory inside of that heap. So essentially you will be able to allocate memory in that specific heap and deallocate the memory. So I really wanted to implement my own sort of allocator for quite some time because I never done that before. So it's very interesting topic for me. Well, I implemented in the past I implemented linear allocators, right? Linear allocators. Essentially, I would allocate like a single array, right? And I'm gonna have something like size, and every time I need to allocate a new chunk, I would basically append that chunk at the end, and then when I'm done doing my algorithm or something like that, I would deallocate everything at once by setting heap size to 0. So, but I never actually implemented an allocator that can also free some chunks of memory and then reuse that memory for something else, right? So this is a little bit more difficult to implement. Actually, I did implement such allocators before, but they can only allocate, you know, chunks of a fixed memory. So creating an allocator with a fixed memory, fixed size chunks allocator. Creating such allocator is actually relatively easy because you can quite easily keep track of the free chunks, and you don't have to spend too much time finding the place for them, like to put. When in case of the allocations with different sizes, it can actually become quite difficult, right? So essentially, yeah, your heap may become fragmented and stuff like that, and you have to also keep track of that. So imagine that you have a heap and you are allocating objects of a fixed size, right? So essentially you have fixed chunks, right? And for instance, you want to allocate a new object and you allocate it here. Then you need to allocate another one, you allocate it here, and so on and so forth. And then you decide to deallocate this specific chunk, right? So you say free. And essentially, yeah, it becomes free. And if you want to allocate it again, you can just iterate from the beginning, find the free chunk and put it there. But that, of course, is of n time, which sometimes you may not want to have. And because of that, you can have a second array that points to the free chunks, right? So at any point, if you want to allocate something, you first check, do I have already free chunks somewhere there? And you can grab them from there. So yeah, you can even grab them from the top of this array, so you don't have to shift anything or anything like that. So working with a fixed chunk, fixed objects is actually quite easy. But what if you have like varying sizes of chunks? So this is where it becomes a problem, right? So for instance, you allocated object of this size, and then you allocated object of this size, and so on and so forth. Then you deallocated this chunk, right? And this particular memory became free. Right, and then you allocated a smaller chunk within this one. So that means if you want to allocate chunks bigger than this one, you have to actually skip that chunk and do something like on that end. So it becomes very very messy very quickly. And this is something that I never done before because I was like scared of that. So, and that's one of the things I wanted to try to do today. So this is going to be one of those allocators that can accept like variant sizes and whatnot, and just, you know, keep track of them. Okay, so we imagine that we implemented the allocator and deallocator for this entire thing. The next thing we can do, we can implement something like gc collect, right? Maybe not gc, but maybe like something like heap collect, which essentially iterates over the heap with a window of 8 bytes, right? So something like this. So here's your heap. Then you look at first 8 bytes, right? Here's the first 8 bytes. Then you look at the next 8 bytes, another 8 bytes, and you have this sort of like a rolling window of 8 bytes, and you sort of scan your heap, right, by 8 bytes. The reason why it's 8 bytes because it's the size of a pointer. And we want to actually scan the chunks that are allocated. We're only looking at the allocated chunks. Right, and we want to find something with those chunks that resembles a pointer to the memory. We're looking for the pointers to the memory. And we're trying to see if that pointer points to something within the heap. Right. And if it points on one of the allocated chunks, right, if one of the allocated chunks has something that resembles a pointer to another allocated chunks, we mark this chunk as reachable. Right, after doing this entire process, we can try to take a look what chunks are unreachable and automatically deallocate them. So effectively implementing our own garbage collector. Right, and again, I also never implemented my own garbage collector before, so I have no idea how to do that, and that's precisely why I'm doing it today, because I want to learn how to do that. So today we're going to do two things. We're going to implement a simple allocator that can work with chunks of various size, that keep tracks of free chunks and whatnot. And then we're going to try to implement a simple garbage collector that scans the heap and tries to find something that resembles a pointer and see if it points to something within the heap. So of course, there is a probability of some data looking like a pointer to something inside of a heap, and thus actually preventing this thing to deallocating. But we're going to assume that such probability is going to be quite low, right? So we can try to maybe, you know, estimate that probability, but I feel like it's going to be pretty low because it's like you have 8 bytes, and what's the probability of 8 bytes combining into something that resembles not only a pointer, but also pointer within the heap? And if that happens, well, there's nothing bad that could happen. Okay, one chunk of memory is not going to be deallocated for some time, but maybe after some time the combination of bytes will change and then it will be deallocated. So I don't think it's that big of a problem, right? I feel like the probability is quite low, but I'm not a computer scientist, so I don't feel like you know, estimating it, but maybe I should estimate it at some point. So another problem is that you won't be able to implement something like sort linked list, right? So because in case of a sort linked list, you basically have 2 pointers that point to the previous one and to the next one, right? But instead of using 2 pointers, you actually use a single pointer, which is basically a XOR operation on both of these two, right? So, and then using like the property of XOR, which is basically A XOR B, and then XOR B is equal to A. Using this property, you can start iterating this list from the beginning to the end, and then from the end to the beginning, however you want. And thus you sort of saving a little bit of memory, you know, on one pointer. But to be fair, well, you have to be, first of all, aware that this is not going to work. Second of all, does anyone use this kind of stuff in production? Like, I keep hearing people talking about sort linked list, but does anyone actually use that? Like, if you are, nobody tries to use them, tries to use like even regular linked list in production anymore, let alone sort linked list. I don't know. In any case, so these are possible concerns that I'm gonna just basically brush off. Maybe there is more concerns, but oh yeah, there is more concerns. So you may have pointers on a stack, right? So essentially you may have something like main, right? And you can allocate some root in here. So it's going to be heap alloc. And you're going to allocate 69 bytes. So you have a pointer that is stored on the stack, rather than in a heap. So after the heap collect scan, the garbage collector will come to the conclusion that nothing points to that specific chunk of memory, and it's going to be deallocated automatically, right? So one of the things maybe heap collect could do is try to scan, on top of scanning the heap, our heap, it may try to scan this stack as well, right? Why not? The same way, essentially. So just iterate through the stack with a window of 8 bytes and just try to find something that resembles a pointer and see if that pointer points to something within the heap. So there are different ways, as far as I know, to find the the stack base in different compilers and in different platforms. So probably our solution is not going to be very cross-platform, but it should not stop us from implementing this thing nonetheless. My goal is to learn how to do things, not to make a cross-platform production-ready product. And yet again, I'm really sad that I have to constantly explain that because some people just don't understand that. Some people don't understand that you not necessarily have to all the time write perfect software first try that works on all the possible platforms. Those people usually don't implement anything useful because they constantly talk themselves away from implementing that because it's not perfect first try and it doesn't work on all of the possible platforms. And because of that, they also try to talk away other people from doing that because, yeah, that's what those people do. I try not to listen to this kind of people. So, yeah, that's basically the idea. That's basically the idea, and let me make a small break, make a cup of tea, and we're gonna start implementing. So the first point in our agenda today is gonna be implementing just a, heap allocation and deallocation, and if we have time, we can try to work with garbage collection. You know what will be even cooler? Try to run the garbage collector in a separate thread, right? So in maybe put some POSIX threads in here. But then the garbage collector has to stop the main thread when it collects everything. So is there something like, I remember that pthreads had something like suspend. They had something like suspend. I remember there was something. Pthread suspend? No, I don't remember. I remember quite vividly there was like pthread suspend, like literally the name of the function. Okay. Oh, okay. So there is something. Like there is resume np and there is suspend. Yeah. Okay. So there is at least something. Resume execution of a thread, continue execution of a thread, and suspend execution. Okay. So maybe we're gonna have a separate garbage collector thread that basically periodically suspends the main thread and just collects something, and then resumes the main thread. So yeah, I don't know. We'll see. Let's make a cup of tea and let's implement basic allocator. All right, let's try to implement heap alloc. I'm gonna ignore any alignment for now, just to simplify things, but maybe later we can take that into account. So for now, I'm gonna try to do like a very simple linear allocation, right? So we want to allocate a chunk of memory of the size equal size, right? So we need to check. Maybe I'm gonna even assert something. It's gonna be 10 that. Heap size plus size is less or equal than capacity. So, and then we're gonna put assert in here. So I kind of want to rename capacity to heap capacity, right? It's not just like any other like capacity. It's specifically heap capacity. So after that, we need to find the pointer, right? Which we're going to return, and it's going to be basically heap plus heap size, not capacity, thank you very much, heap size, and then we add the size of the chunk to the heap size, and then we just return this result. Right, this thing is going to be unimplemented for now, something like this. To do heap free is not implemented. It's not implemented as well as heap collect. There we go. So, yeah, and here we're allocating 69 bytes. So as far as I know, we don't have booleans, so let's actually include std_bool. There we go. And okay, so what I want to do in here, maybe I'm going to just allocate a little bit of memory and maybe initialize it with something, I don't know. Maybe we're going to do something like this, 26, right? So, and then I'm going to iterate from 0 to 26, right? So then I'm going to assign I to I plus A, right? So, and after that, if we take a look at the heap memory, we should see the English alphabet starting from the beginning to 26th byte of the memory. So I have no idea what kind of example should I come up with to test this kind of stuff. It will be also kind of good to have a make file where we can test things, with which we can build the project. So let's quickly do that. So it's going to be cc. Maybe I want to put it into the variable. This is a c flags. Heap main.c. Do we need any libraries? I don't think so. I don't think we'll need any libraries for now. Later we'll probably need POSIX threads, right? So, and in that case we'll have to link with a special POSIX thread library. All right, so it's going to be WALL, WExtra. So the standard that we're going to use today is going to be C11, and we're going to make it pedantic. There we go. So if we try to build this entire thing, let's see what's going to happen. Okay, so there is a couple of unused things in here. It's going to be PTR, right? There we go. Okay, so maybe it would also make sense to actually build with debug information. Yeah, I probably want to rebuild everything from scratch. There we go. So let me go to here. It's going to be gc and gdb heap, right? So I'm going to break on main. And I'm going to run the application. Okay, so what do we have in here? We have a root, we just allocated root. I might as well actually display root just in case. And as we go, as you can see, the heap, yeah, it points at our heap, and heap is being filled up with the English alphabet, right? It's just like we allocated a chunk of memory and we're filling up that chunk of memory with English alphabet. Nothing particularly special, right? So that's it. So we managed to allocate memory, but we don't know how to free that memory yet. Right, so there is no way for us to free that memory. Heap free, heap free root. Right, so if you try to free that memory and just run this entire thing, it will assert saying that this thing is not implemented. All right, so let me think. I probably need to open my paint and draw a little bit. All right, so essentially here's our heap, right? Here's our heap, and we allocated a chunk of memory, right? So there's 3 situations that may happen when you try to deallocate a piece of memory. So first situation is you try to provide a correct pointer, right? Correct pointer. What is going to be correct pointer in this particular situation? Well, it's going to be the pointer which points at the thing that was returned by heap alloc, right? So heap alloc returns this thing and you provide this thing, so it was deallocated correctly. Second, it might be invalid, right? And there are two kinds of invalid. Invalid within allocated memory, alloc memory, right? So somewhere here, and invalid outside, invalid outside of allocated memory. So it's going to be somewhere here. Does it even matter to distinguish these two things? I think for our case, it doesn't really matter. You either provide the correct pointer that was allocated or you provide incorrect one. So yeah, and if you provide incorrect one, we just should throw an error or do something about that. I don't know. Yeah, I think we can just crash if you try to provide an invalid pointer. So that means we need to keep track of sort of allocated chunks, right? So we need to keep track of allocated chunks. On top of keeping track of where they start, we might as well keep track of their sizes. I think it's going to be actually pretty useful. So let's actually define some sort of a structure. Let's call it something like heap chunk. Right, so I'm going to put this thing in here, and it's going to start at a particular pointer, and it's going to have a particular size. Right, there we go. And we are going to have an array of such chunks. Right, so it's going to be heap chunk. Heap, but these chunks are specifically allocated chunks, right? So it's going to be heap alloced chunks. Alloced. So, and obviously this array is going to be sort of fixed. What's going to be the capacity of that array? So we can treat this array as sort of metadata for the memory we are allocating, right? So it's going to be metadata. So heap alloced chunks capacity. Maybe I'm going to just call it cup. Right, and to be consistent, maybe it would make sense to rename heap capacity to heap cup. Right, there we go. Alloced. So does it make sense to actually prefix them with chunks? Yeah, I don't like long names, to be fair. I don't really like long names. So we're going to call them heap alloced, and this is a heaped alloced capacity. So this is heap size, basically the end. And we also need to keep track how many of heap alloced we have in here, right? So because we're going to be appending them at the end. Right, on top of like having this heap, we're going to have array of fixed size elements, these chunks, right? So in each individual chunk, right? So this is a chunk. Chunk is going to consist of two things. It's going to consist of a pointer, right? Which points at the beginning of this thing, and the size, which determines how big of the chunk it is, right? And you're going to have a lot of these sort of like meta information chunks that point to different things on the heap and determine their sizes and whatnot, right? So we're gonna have like sort of like a metadata table. So that's essentially what it is. It feels like we'll need something similar for freed chunks as well. And when you try to allocate something within the heap, first we're gonna look up into the array of free chunks, right, and try to find something that fits the best for the memory that we're trying to allocate. And then what's interesting is that if you have a free chunk, right, that has this particular size, and you want to allocate this amount of memory, and you don't have any other chunks where this thing fits, you're probably gonna like allocate this chunk, and then you'll have to create a new free chunk of this size, right? And you will have to add it to the list of the free chunks. This is rather complicated. I start to understand why Mallocing memory is so slow. Because you need to like build sophisticated data structure that keeps track of the chunks of the heap and stuff like that, and heap can get fragmented and stuff like that. Holy shit. Is it even worth it? Let's just like ditch all of the allocators and use only linear allocators or something. Okay, but I mean, nobody does that on that level, so it's a solved problem, am I right? Just call malloc and forget about it. Okay, so we're gonna have this kind of thing. This is the allocated chunks and whatnot. The capacity, what's gonna be the capacity? Okay, heap allocked cap. Let's say that for now is gonna be like 1024, why not? Okay, when we're trying to allocate a chunk, so here's the beginning of the chunk, and here is the size of the chunk. So, and essentially we can just construct something like heap chunk, right? And it starts at the result, right? I don't think it's called starts. I think it's just called start. So it's going to be start, and the size of this thing is equal to the size that was provided by the user, right? So here is the chunk. Here is the chunk, and then we need to append that chunk to the heap allocked, right? So we need to append it to the heap allocked, but also that means we need to assert that heap allocked size is less or equal heap allocked capacity, right? So something like this. And after that, actually, less, yeah, it has to be less. Heap allocked, heap allocked size plus 1 chunk. There we go, there we go. So yeah, this single allocation actually allows us to see all the chunks. So it would be kind of cool to have some sort of way to dump allocked chunks. So maybe we're gonna implement a function, something like heap dump allocked chunks, right? So it's not gonna accept anything, but the only thing it's gonna do is gonna just iterate through all of the allocked chunks and just print them somehow. So let me see. Heap allocked chunks, right? Heap allocked size, right? And for each individual of them, we're going to be printing, I suppose, their position, their start. So this is where they start, and their size. Okay, so heap allocked I start. There we go, and heap allocked I size. There we go. So this is what we got. So maybe it would also make sense to do something like allocated chunks, right? So these are the allocated chunks. So maybe it would also make sense to actually print the amount of them. Heap allocked size. There we go. So yep. And before trying to free anything, we're gonna just like do heap dump allocked chunks, and let's see how it goes. So it does not even compile because I forgot a semicolon. All right, so okay, so we have allocated chunks, and as you can see, we allocated only a single chunk. This is where it starts, and the size of it 26, precisely how much we allocated in here. Right, so we can try to do something like more interesting than that. For instance, we can allocate them in a loop, right? So it's going to be I0 to 100, right? And essentially heap alloc I. So by the way, if you try to allocate the chunk of the size 0, is that a valid thing to even do? Huh. Okay, so in our case it is valid, and it will basically allocate you, yeah. So it will give you a pointer, and then you will try to allocate something else, and it will give you the same pointer back. So it creates some sort of a paradox, and also you will end up with an empty chunk, essentially, right? You're gonna end up with an empty chunk, which is like really invisible, very thin. So let's actually give it a try and see what's gonna happen. So this is a root, and we don't even have to free anything in here. All right, so yeah, there we go. So you have the first chunk that starts here, and it's size 0, and the next allocation returns you absolutely the same pointer. unfair, right? So I don't think it's a correct thing to do, but everything works correctly here. So as you can see, we have 100 chunks, and each individual actually like spaced apart from like by their size. So that's actually pretty cool. It would be kind of cool to actually visualize the heap at some point somehow when we start keeping track of the free chunks and whatnot, right? So maybe generate some sort of an image that basically draws the strip of the memory, like which is a heap, and red spots are going to be allocated memory, and then like other colors going to be deallocated memory, and we can clearly see how the heap is fragmented and whatnot. So that would be actually kind of interesting in my opinion. That would be kind of cool. All right, anyway, so this is probably not the correct thing to do. How does malloc even handle this situation? Let's actually find out. So in malloc, allocate size byte and returns a pointer to the memory is not initialized. If size is 0, then malloc returns either null or unique pointer value that can later be successfully passed to free. Unique! It returns unique ones. So as you can see, here's the problem. In our case, it does not return a unique pointer. And yeah, that's very interesting actually. So to be fair, I think it would be nice to handle size 0, because the programmer who uses the allocator may have edge cases when some size is 0, and it would be easier to handle these edge cases if malloc and free, malloc just accepted size and free just accepted a pointer from the malloc that accepted size 0. You know what I'm talking about? So yeah, that way the programmer shouldn't actually handle these corner cases themselves, right? So that's kind of interesting. So what does it return in my case? Oh, and by the way, null can be also passed to free, right? Null can be also passed to free, and probably because of the same reason. That's really interesting. I'm learning things. I really love when I start learning things. Okay, so let me see what's going to happen if you try to malloc like size 0. So it's going to be printf, but it definitely does not crash, right? It definitely does not crash. Okay. So malloc, implicit declaration, let's include stdlib, and it returned a unique value. That's very interesting. Okay, so, well, we don't know if it's unique or not. Let's actually do a couple of iterations. 0, let's actually do 2 iterations, right? So we're gonna leak a little bit of memory. Okay, so it does in fact return a unique value every time. That's actually kind of cool. But can we return a unique value every time? And what's that value has to be? And what's going to happen if you try to access that memory? So if you know what I mean. So it's going to be void. Let's pull it char p. So it's going to be p. And then I'm going to try to set, actually, let's just dereference it as it is and set to 69. What's going to happen? Well, it is, at least the memory is mapped, right? So at least the memory is mapped, but it's probably something that I shouldn't even touch, right? So I don't know. So in my opinion, it would be better if it returned null. So then if you try to dereference it, your application will crash. But then on the other hand, null is not particularly unique, and you may want to have a uniqueness if you store something, if you rely on malloc always returning like unique values or not. So I don't know. So the easiest solution for me right now is going to be just return null in case of the 0. Because that way I just don't have to implement too much stuff. Okay, if size is greater than 0, right, we're gonna do this thing, this entire thing. There we go. Otherwise, I'm gonna just return 0. There we go. So that's the easiest thing for me to do. Actually, not 0. I have to return null, right? So it has to be null. Okay, so let's actually go back in here and let's allow allocation. Oh, look at that. Right. So we did 100 allocations, but the amount of chunks in 99, because essentially allocating a chunk of size 0 was skipped, right? It was straight up skipped. Nice. So that's precisely what I wanted to see in here. All right. So here's an interesting thing. We might as well do the following stuff. We can save the pointer, right? And on each even allocation, we're gonna instantly try to deallocate that thing, right? Yeah. So that way we're gonna be sort of fragmenting the heap. So there is allocation, and on some allocations, like on even allocations, we instantly deallocate that chunk as well. All right, so and then we're gonna dump allocated chunks, and right now, as you can see, free is not even implemented. So how are we gonna be working with all of that? First of all, we need to know whether the pointer is valid or not, and right now the easiest way to know that is essentially by iterating through all of the existing chunks. Right, so because of that, the complexity of free is going to be O of allocated. Yeah, let's call it O of allocated. Allocated is the amount of allocated chunks, right? So it's going to be at least that heap allocated size plus I, and if heap allocated I start equal to pointer, that means we found this entire thing. And now we need to somehow mark it as deallocated. So that means we need to keep track of the sort of free chunks, right? So okay, so maybe we can even reuse the same data structure, so we can keep track of freed chunks as start and their size. Why not? So okay, so let's allocate the array heap chunk heap free, and we already have a heap free, which is a function. Damn. How do you spell freed? Do you spell it as this? Or usually it's an ed suffix, right? How do you add ed suffix to something that ends with double e? Do you add the third e? I don't speak English. Don't look at me like that, all right? English is my second language. I don't know. Freed. Do you have double? I suppose you don't add the third. Why? God damn! Why? Why don't you add the third e? I think it would be actually quite funny. To make free as from confinement or oppression, freed. Okay, so makes sense. All right. So because we have allocated and we have freed. Right, makes sense. Cool. So it's going to be heap freed cap, and it's going to be something like that, and freed. So the capacity of freed is going to be the same as the allocated capacity. Why not? Why not? And essentially, if we find the pointer that you're trying to allocate, what we're going to be doing is transferring that pointer to list of freed chunks, and that creates another interesting problem, right? So there's so much fragmentation going on. Okay, so here is a heap, right? So this is a heap. All right, and you have a bunch of chunks in here, right? So which are allocated, right? So then you have an array of allocated, which is essentially, in this particular case, is going to be array of 3 elements, right? So I'm going to actually sort of indicate that this is the edges of the element, and within those elements you keep track of the starts of these allocated chunks, right? So these are the starts, and these are the sizes, right? So this is going to be size 1, size 2, this one is the pointer that points here, and this is a size 3. So essentially, now you want to deallocate specifically this chunk of memory, right? So what you're doing, right, you're finding, first of all, in O of n, in a linear time, you're finding this thing in here, right? You're moving that stuff into the array of freed, right? Which is also array of chunks, So now this array is going to be pointing to this thing. Right, and you have a hole in here. So you're starting to have a hole in here, something like this. And since you essentially moved the alloced meta information of chunk to the freed one, you have a hole here as well. So apparently array is not particularly good way of keeping track of these chunks. A better way, in my opinion, would be some sort of a hash table, right? So in the case of a hash table, you would quickly look up pointer as a key, right, and then just move it to the freed one. So I think it would be way better. Unfortunately, we don't have a hash tables in C. Maybe I have to switch to C++ or implement hash table myself, but I don't really want to implement hash tables right now. If we're not going to implement hash tables, right, and we're going to roll with the linear data structures, so I'll have to implement like move, basically move this thing by its size. And in that case, I think it would be easier to just use mem move, right? So it's going to be just something like mem move. Right, but mem move is really inconvenient because it basically works with bytes, and you constantly have to keep like remember about that, and it's like yeah, it would be way better if it was some sort of a hash table or at least a tree. And if it was a hash table, the allocation in that sense is going to be O of 1 amortized, right? So because you need a single lookup in the table, so lookup is going to be O of n amortized, and inserting a new entry into the table of read is also going to be O of n amortized. So is there something like so hash table in C? Hash table in C, C++, not tutorial, but maybe on the GitHub, maybe there is like a header only. Hash table implementation in C. Something in STB style. I wonder if STB has something. So let's take a look. Nothing's STB. Do you have hash? Okay, type safe dynamic array and hash tables for C will compile in C++. Oh, wait a second. STB straight up has hash tables. I didn't know that. That's actually pretty cool. Okay, maybe that's something we can use. That's pretty cool. You know what's funny is that the hash tables also probably need allocation, right? Yeah, because you're going to be stretching. If you're going to have a lot of memory, you'll have to stretch your hash tables, but you don't have an allocator because we are implementing the allocator. So that means you need a hash table that has a fixed size. The same way, yeah, so that is funny. Okay, so like for a hash table, you need a memory allocator, but you are implementing memory allocator. Like, what? Yeah, I guess you can have like a fixed hash table. And stuff like that. Maybe implementing fixed hash table is not that hard. You just allocate a fixed array, then you use a pointer as the key, and you always mod that key. And collisions are basically resolved by open addressing, but I don't think with open addressing it's going to be easy, because then like how do you remove things from there? Essentially you will have to mark these things as dead, right? The removed elements as removed, and then yeah, it's not going to be particularly great, because you can, but yeah, it would be better to just have like linked list or something like that. But again, you kind of know that all of your keys are unique. That's what's interesting about this thing. Your keys are kind of unique. Maybe you can exploit that fact. Yeah. So here's the fun fact. Everything is unique unless you provide size 0, but in case of a size 0, we return null and never create any of the heap chunks. We never create any of the heap chunks. But again, if you mod the pointers, right? If you mod the pointers, they may collide for, you know, for different reasons. When will they collide? Okay. I think I need to think about that one, actually. So let's make a small break. I'm gonna refill my cup of water and also think about it. And after the break, we will come up with something. Though if I won't come up with something, we can just use like a linear data structure. And every time we need to remove the heap chunk, I can just like, you know, shift everything. It's not that big of a deal. Right. So I just don't want to use data structures that do allocations, because we are implementing the allocator. So if we're going to be using something that uses allocations, how are we learning anything? You know what I mean? So I could just like switch to C++ and start using something like unordered map or something, which is essentially hashtable, right? And just like do a pointer from a pointer to the size, right? So it's going to be from the pointer to the size. But again, this thing probably allocates the memory. So when the question is like, if it allocates the memory, how that allocator is implemented, right? You know what I'm talking about, and that's why I don't want to do that. And I wonder if the classical implementations of the allocators have like, you know, dynamically growing metadata, or maybe metadata is actually fixed. So what's interesting is that I can see the metadata getting bigger because of the like a lot of small empty chunks, right? So as you free more and more small chunks, you're going to have a lot of data in here, but a lot of these chunks are going to be consequent. You know what I'm talking about? So at some point you would need to do some sort of a cleanup step that iterates from like through all of the free chunks and finds the consequent free chunks and just merges them together into a single chunk. You know what I mean? So yeah. And it should be relatively easy, I think. You just sort, right? You just sort the this array by a pointer, and then linearly iterate and see if the chunk is consequent, and you just merge it into like this entire thing into a single one. So yeah, and that way, maybe if you do that, you constantly sort of compress your metadata, right? So the metadata starts to grow, you just clean it up, compress some of the consequent chunks, and it doesn't really grow that much, right? Because at the beginning of the allocator, right, you have the whole free heap, so you have one single huge free chunk. Right, so that makes sense. Okay, that's actually pretty cool. Anyway, let's make a small break, and I'm gonna make a cup of tea, and then we're gonna try to implement something. Okay, I got an idea. So what if we keep the chunks sorted by a pointer? Right, so that way we can quite easily query them in log n, right? So it's going to be query. How do you spell query? I think this is how I spell it. It's going to be log n. Then insert. To insert a new element into a sorted array, you need to O of n, right? So essentially, you start at the beginning, right? And then you basically swap elements until the element that you're trying to insert fits in that specific place, and it's going to be O of 1 in worst case scenario. And remove is also going to be O of n, right? So it's not particularly great data structure, but I think it's going to be fine for now, right? Basically sorted array of chunks. Maybe I'm gonna even have a separate structure for this kind of thing. So we have a heap chunk, and maybe we're gonna have a heap chunk list, right? So essentially I'm gonna take this thing and turn it into a data structure, right? So it's going to be something like heap chunks, and the size of this entire stuff is basically heap alloced cup. Okay, so I think we're gonna reuse the same data structure for allocked and freed chunks. And on top of that, I think like the name heap chunk list is too long. So I think I'm gonna do the following thing. I'm gonna rename this to a chunk, right? So this is a chunk now. And in here, right, this is gonna be just a chunk list. So heap is gonna be that. And then we're gonna have something like chunk list. Alloced chunks, right? So here's alloced chunks, and it's going to be just like chunk list, and it's going to be 0 initialized. So there we go. And we're going to have another chunk list, which is freed chunks. All right, so something like this. So the reason why I wanted to have as a separate data structure is because I want to define operations on it, right? So it's going to be something like chunk list. Find, and you would provide the pointer, right? You would provide the pointer, and how we're going to indicate that we found something. I think we can return an integer, right? So it's gonna be essentially a pointer, an index in the array, and if it's negative, it's going to be indicating that there's no such chunk in there, right? So something like this. So this is going to be the first operation that we want to implement. So it's going to be a to-do, chunk list find is not implemented. So the next, another operation is going to be something like chunk list remove, right? And by the way, I forgot to accept chunk list in here. So this is going to be a list. And since find does not modify that list, we're going to actually pass it as the const pointer. So then we're going to have a remove, right, which passed by a mutable pointer, and what we're going to be removing in here is the index, right? So it's going to be something like index. So in that case, maybe the index has to be size t, but because it doesn't really have to be doesn't need to have an indication that it's missing or something like that in this particular case. Okay, so let me put it like this: list remove, right? So, and another operation we want to have is an ability to add things, right? So it's going to be insert chunk list, and what we're going to be inserting in there, we're going to be inserting the pointer, the new pointer, and the size. There we go. And of course, this thing is not implemented yet. All right, it's going to be insert. There we go. So this is what we want to have in here. All right, so here's the heap. Here is the allocated and freed chunks. So when we allocate something, right, we don't have to do this kind of stuff. We just allocate the memory, and then we do something like chunk list insert alloced chunks. So this is a locked chunk, and we're providing the pointer, so it's called result. I think I want to call it pointer ptr because it's called ptr everywhere else, and then the size, and I can remove this entire stuff. Okay, that's kind of cool. So first I'm trying to allocate the new thing in here, and once it got allocated, I'm adding that chunk to the list of allocated chunks, and that's pretty much it. That's pretty much it. Okay, so a dump alloced chunks. To be fair, maybe we could transform this entire thing into a chunk list method, if you know what I mean, right? Because then sometimes you may want to dump not only alloced chunks, but also freed chunks. And we're reusing the same data structure for all of them. So it's going to be something like chunk list dump, right? So this is going to be chunks, and maybe we need to accept chunk list. So let's actually accept chunk list by a constant pointer, right? So, and in here we're dumping count, then we are iterating the count, right? So here's the count, and in here we do list chunks, and there we go. All right, looks good to me. So what else do we have in here? So free, we don't know how to implement free yet. So I'm gonna just put assert in here, something like this. Heap free is not implemented yet. So I'm just thinking what would be better to do here. it would be better to have some sort of a function to do const char message fprintf std error. Yeah, I wish I could actually also specify the position, the place where all of that is located, but it's not that easy. So we're gonna do something like this to do. Right. So in this one is going to be just a message, right? So we provide this message in here, and then we exit with 1, right? So we're going to basically crash this entire thing. Maybe we're going to even abort, right? So sig abort and stuff like that. But it would be also kind of cool to be able to print the file and the line where all of that is located. And if we try to use file and line macros, it will point at this specific place, right? Which is not particularly convenient. So to sort of circumvent that, we can turn to do into some sort of a macro. Let's actually define it as a macro, and it accepts a message. And now we should be able to do something like do while 0. 1, 2, 3, 4. And let's actually put slashes at the end of all of these things. There we go. So that way we should be able to do the following thing. So I can just do to do chunk list find, right? All right, so that's a little bit better, I think. To do chunk list insert. It would be nice to also have a func, I think. Maybe we can use a func in here. You know, yeah, so what about if we just call it a to do like this, right? And then we can say this is not implemented yet. And in C, is there something like function? Okay, so there is a function. Is a pre-standard extension that some C compilers support. In general, you should use func, which is supposed to only use a function. Okay, so we can try to do func then. So, and remove the message completely, so it's gonna be func. Okay, so maybe I'm gonna actually keep it like that. All right, so maybe that way I don't have to do any of this stuff anymore, which is kind of cool. So that means I can just keep copy pasting this stuff. Yeah, because I'm kind of tired of, like, you know, copy pasting the same thing over and over again. Alright, so if I try to recompile this entire thing, it does not even compile properly. Expected, but got... okay, so that means I need to put func somewhere at the end. Okay, I see. So func should go here. Right, here's the func. Do we need anything else? Type int. Okay, so this line for some reason is int. I don't know why though. And you have a couple of... Alright, and define reference for heap dump. So this is another problem, but maybe we can do something like this. Alright, so heap free is not implemented, and okay, that's actually pretty cool. To do. But to do is too general thing. Maybe I'm gonna actually replace to do with unimplemented, right? And boom. And maybe because of that, it would make sense to get rid of the parentheses. Let's get rid of the parentheses. Boom. So, all right, heap free is not implemented yet. Nice and perfect. So should have implemented something like this long time ago. Nice, 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 nice. So I'm not sure if to do is generally a good idea. All right. So let's go through this. So some of these things. unused parameters. Huh. You know, there's also a pretty cool idea is that I can put this thing like that and never use anything. So that way I sort of, it's probably not gonna work. Yeah, it's probably not gonna work because these parameters are still not used anywhere here, right? So they're still not used anywhere. But maybe, nah, it's too much. I think I'm bike shedding at this point, so I don't know why I'm bike shedding. But yeah. PTR size. Sometimes I have to remind myself that this is a bike shading. Please stop. Void PTR. All right. Unimplemented. Undeclared. Oh yeah, of course. Okay. Cool. Free is not implemented. Now, but why free though? Because I thought if I try to do heap allocation, right, I will have something like chunk list insert, and chunk list insert is also not implemented. So why we hit a heap free? Oh yeah, because we also try to free it. Okay, so let's actually try to first do this thing, and there we go. So chunk list insert is not properly allocated. Okay, so let's try to do the following thing. We're gonna assert, right? We're gonna assert that list count is less than. Let's actually have this as a capacity. So it's gonna be chunk list cap. So there we go. A locked cap, and this is going to be chunk list cap. There we go, a chunk list cap. So when I'm inserting the new thing in here, we want to make sure that it's less than chunk list cap, right? Something like chunk list cap. And what we're going to be doing in there, we're going to be just inserting this entire thing at the end, right? We're going to be inserting it at the end. List chunks list count equal equal PTR, I suppose. It's actually start PTR, and then size, maybe because of that I want to call this start, right? So for the symmetry and stuff like that. And after that, I need to start sort of moving that thing into the appropriate place, right? So essentially, you have an array that is already sorted. This entire thing is sorted. And then you append a new element in here, which makes this thing not sorted, right? So this part is sorted, but you added a new element, it's not sorted. So what do? You start iterating by pairs and going to the left. You look to the previous element, right, and see are they sorted, right? Are they sorted? If they're not sorted how you want, you just swap them around and move to the next one, to the next sort of pair. And you keep doing that until you find the elements, you find the place where this condition holds true or something. You see? So that's basically the idea. So you put the element at the end, and then you're just trying to feed it, constantly swapping things around until, you know, it fits there perfectly. And that will take O of n, right? That will take O of n. You can try to basically put this thing in at the end and then sort this entire part, but your sort is going to be n log n, right? But inserting a new element like that is going to be O of n, right? So yeah, I don't know. It just depends on what you want to do. But in our case, do we want to go like a fast route? Maybe. I don't know which one is going to be interesting. So if I remember correctly, in C you have Q sort, right? So you just have a Q sort. All right, so we're gonna start iterating. from list count, right? From list count up until I is greater than 0, right? So if it becomes equal to 0, if I becomes equal to 0, that means we're already pointing here, and there is no previous element, so it has to be strictly greater than 0. Right, and then we're decrementing I. Cool. Now, what we're trying to check in here, also there should be another condition, and list chunks I ptr, so this is the current one, has to be less than list chunks I minus 1 ptr. So if the previous one is bigger, that means we're not in our right place, right? So we're not in a correct place. So let me actually put this into like a cases style for loop. There we go. Here's a cases style for loop. And because of that, we need to swap these things around, right? So how we're going to be swapping them? So I need to have a chunk. So this is the temporary chunk, and I assign chunk I to the temporary one. Then I take the previous, the current one, and I assign the previous one like this, and the previous one is going to be equal back to this chunk. So this is how I'm going to be swapping them, and I'm going to be doing that, you know, until I find the appropriate place. So if you are inserting in a completely new chunk, right, a completely new chunk, so that means you already going to be 0. I is going to be equal to 0, and everything is going to be fine. Okay, so after that I need to increment the counter, right? So now the counter is incremented. Cool. So this is how we insert a new element in there. Isn't that cool? All right, so let's try to compile this entire thing. And what do we have in here? So this is a PTR. It has to be start. We call this thing start. So this is a chunk and yeah, everything's okay. So allocation went well, and after that, what I want to do, I want to do something like chunk list dump, right? And what I want to dump there is alloced chunks, and I'm going to provide a pointer in here. So here are alloced chunks, and as far as I can tell, they're sorted in, you know, in the correct order. So okay, that's pretty cool. Again, we were trying to implement the free, right? So, and free is not implemented yet. So how we implementing a free? We need to first find the chunk, right? We need to find the chunk that you want to allocate. So chunk list find, we provide the list of allocated chunks, alloced chunks, and the pointer, right? There we go. And this entire thing should return us an index, right? And if the index is less than 0, right? That means something went wrong. We're gonna just, you know, assert that everything went okay in here. All right. So after that, we want to grab that chunk and add it to the list of free chunks. So we're gonna do something like chunk list insert freed chunks. And how we're gonna be inserting that? We're gonna be inserting it as alloc chunks, chunks index, right? So we're using that index. After that, I want to remove, right? I want to remove that thing from the alloced chunks. So I'm removing that index, and I specifically converting it to size t. I know for a fact that it's going to work because index is greater or equal than 0, so it is easily convertible to size t. So, and also don't plan to modify this entire thing. So I'm going to mark it as const. All right, so we have a heap free, and what do we have in here? Alloced chunks. So this is not a pointer, I suppose, right? So the index, incompatible type of 2 of list insert. Why? Oh, this is because it doesn't accept Yeah, okay, it accepts pointers and shit. Okay, so that means maybe we can do something like start, right, and then size. Not particularly convenient, but I mean, when we are allocating a new thing, it's just like, yeah, that's what you want to do anyway. All right, so chunk list find is not implemented. Okay, so chunk list find is not particularly implemented. So how we can do that? We can use binary search to find an element in a sorted array. Do we have a B search? Yeah, we do have a B search. Nice. So you're searching for a key, then you provide the base, and also you have a special function that compares the keys and whatnot. Searches an array of a member. So okay. Searches an array of an member object, the initial member of which is pointed by base, for a member that matches the object pointed by key. The size of the member of the arrays is specified by the size. Okay, but what's interesting is that we're measuring them by the pointer, so which makes it kind of difficult, and it returns a pointer. All right, so I don't really want to implement my own binary search, so I'm gonna just like do it like this. I'm trying to find a pointer. So they have to have the same types, unfortunately. They have to have the same types, and maybe it's not that big of a deal. You know, I may construct a key like this. So this is going to be the key, and in the key, I do start equal to pointer, and everything else is going to be just initialized as 0. So then I can just provide the key. So the base in that case is going to be list chunks, right? So here's the chunks. The amount of elements is going to be list count. The size of the element, right? The size of the element is going to be size of list chunks, I said, 0. And we need to have a special comparison function. Okay, so let's implement something like int chunk start compare, right? So, and here we're going to accept 2 pointers, chunk A and const chunk B. There we go. So, and in that particular case, what we have to do, so it has to return 0 if they're equal. So the semantic of this kind of compare function is basically A minus B. So essentially what we need to do, we need to take a start and subtract like B start from it. And I'm not sure if it's going to work really well. So if it's going to be negative or not negative or something like that, I don't know. But we can try that. We can at least try that. So, and this is where we're gonna provide the chunk start compare, right? Chunk start compare. All right. So, and then it will return us the thing, right, indicating whether it found something or not. So return matching. Okay. So result. Right, so this is going to be the result, and if result not equal 0, we need to return an index, right? We need to return some sort of index, and if it's equal to 0, we need to return -1, right? So we're indicating it like this. So then I assert that the list chunks is less or equal than result. That's quite important, because after that I'm going to be taking result and subtracting chunks, right? So that will give me sort of the byte at where it all starts, and then maybe I want to sort of divide all of that by the size of the list chunks. Not sure if it's a generally good idea, but maybe it is, because I only care about the index, and that could be the index right here, right now. So maybe that's a good way of doing that, but I'm not 100% sure. And I also need to double check if this thing actually like returns like -1 or like 0 or 1 or something like that. So let's do something like this. We're gonna allocate an array on the stack of 2 elements, right? So it's gonna be A and 2 elements, right? And what I want to do, I want to just print this entire thing as D. So it's gonna be A 1 pointer minus A0, right? So this thing should be positive, right? So if I try to build this entire stuff, O foo C, and then I run this entire thing, it is 1, as you can see, right? And if I actually swap these indices around, I hope it's gonna be negative. It's perfect! My god, it is precisely what I wanted to have. Thank you so much. I'm super happy. Okay, so if I go in here, all right. So then we're finding this entire stuff, and there we go. Huh. So hopefully I didn't fuck up any math in here, but yeah, let's give it a try. So I might as well try to like use 10 allocations, so it's a little bit easier to work with, and let's see what's gonna happen, right? So it's gonna be make minus b, and doesn't even properly compile. Okay, so this is a pointer, right? So should be pretty straightforward. Anything else? Pointer of type void is used in subtraction. Ooh. Okay, so maybe we should actually treat them as pointers to char, because that's precisely what we're talking about, right? So when we're talking about chunks, we're talking about chunks like of bytes and whatnot, and passing argument of incompatible pointer type. So expected comp fnt. Can I actually? I mean. Well, sure. Okay, buddy. Okay, so I can accept const void if you want me to. Sure. Const chunk a chunk, and I'm gonna just like, you know, explicitly convert this kind of stuff. There we go. Are you happy now? Hope you're happy now. Okay, so what do we have in here? So comparison of a distinct pointer. Okay, so maybe because of that I want to actually reinterpret this pointer. So didn't help. Because it's a pointer to chunk. All right, and index turned out to be less. So when I was trying to. All right, that is very interesting. So the question is what the index turned out to be. So let's see, it turned out to be -1 precisely, and the only reason it might turn out to be -1 is because we couldn't find anything in there. We just couldn't find anything, so it was not correct whatsoever. Was not correct whatsoever. All right, so let me make a small break, and after the break we'll try to find out what was the problem. Okay, so I think the problem here is that I need to swap these things around. So the semantic of the compare function is that like you subtract the second one from the first one. I think, let me double check that actually. So compare. So the content of the array should be in ascending, ascending, sorted order according to the comparison function referenced by compare. Compare routine is expected to have 2 arguments which point to the key object and to an array member in the order and should return an integer less than equal to or greater than 0 if the key object is found respectively to be less to match greater. Well, the semantic is usually like you just basically subtract the first one from the second one, and it didn't help whatsoever. So that's very interesting. So I wonder. Well, yeah. So isn't it? Well, yeah. It should be fine. Why it didn't even try to find anything? This is so weird. Maybe I shouldn't use binary search, but I'm already using it, so there's no point in denying it. There's no point in denying it. Okay, this is really weird. Let me try to figure that out super quick. I'm dumb. All right, so the problem was quite simple. So where is the index greater than 0? So essentially we are iterating from 0, and first we're trying to allocate 0 bytes, which results in a null, right? And then I'm trying to free the null, and I don't take null into account because it's not available in alloced chunks. So yeah, I think I'm starting to understand why malloc in my environment, instead of returning null, returns a unique pointer that you can then free. Because I think effectively what it does, it adds the chunk so you don't have to check whether it's null or not, or something, I don't know. But it still checks for null because you can still free the null. So essentially what we need to do in here is check if it's not equal null, and only then try to do this entire stuff, right? So basically we're allowing freeing the nulls. And interestingly enough, so let me double check the comparison function. So if I remember correctly, if A is less than B, so that means it has to be negative, right? It has to be negative. So A less than B, that means this thing has to be less than 0. So effectively we want to subtract things like that, right? So effectively we're subtracting things like that. All right, and apart from that, everything's okay. So the only problem is that I forgot to handle the situation when you're trying to free the null. So yeah, let's actually try to recompile this entire thing. Remove is not implemented. At least we got a little bit further, right? At least we got a little bit further. We have insert now, and now we need to just remove the thing. So first thing we're gonna do, we're gonna assert, right, that the index is less than least count. Otherwise, it is not a valid index whatsoever, right? It is not a valid index. So after that, we just need to, you know, just remove that element, I suppose. What's going to be the easiest way to do that? Maybe something like mem move, but it's kind of a dangerous operation, and I'm always scared to use it. So maybe we can do that manually, right? So maybe we can do that manually. We can start iterating size t from the index up until, I guess, the count, right? But we don't want to hit the last element because we are going to be looking at the next elements. So that means we have to do something like -1, and it's going to be plus I. And essentially what we're doing in here, we're taking the chunk, right, the current chunk, and assigning the next chunk to it, right? So it's going to be +1. And after that, we do count. -1, there we go. So right, effectively we have something like this, right? And we need to remove this element. So we keep iterating up until this point, assigning this thing to here, then this thing to here, and so on and so forth. And then we decrement and count by 1, and this is how we removed it. All right, so insert is O of n, remove is O of n, lookup is log n. All right, that's fine. Chunk s. Okay, so look what we got. These are the allocated chunks, right? So we have only 5 allocated chunks. So that means the rest of the chunks have to be deallocated ones. So let's actually print them. So it's going to be freed chunks. There we go. Oh yeah, it's actually 4 of them because 1 chunk was never allocated, and it's the 0th one. It's the 0th one. So here's the interesting thing. How would you implement the malloc feature the malloc feature when it returns a unique pointer when you try to allocate size 0. That is actually rather interesting. How would you do that? So you need to have a pointer. You need to have a pointer outside of the range of the heap. Right, it has to be somewhere outside of the range of the heap. So let me actually try an interesting experiment, right? So it's gonna be foo c, and I'm gonna include stdio, right? So then it's gonna be stdlib, and here is the thing. I'm trying to allocate, rather mallocate, 1 byte, right? So it's gonna be 1, and this one is gonna be p0, right? And let's just compare them. Let's just compare them. It's gonna be p0 is going to be equal to that. P1 is going to be equal to that. All right. I wonder if the order matters in this case. Maybe it doesn't matter. Well, it always does, because I mean allocation modifies the state of the heap, so order will always matter no matter what. Foo c, and let's just try to run this entire thing. Okay, so can we tell it is bigger? So this thing is a little bit bigger because 40, so they are kind of the same, so they have the same prefix, right? Yeah, they have the same prefix. So, and this one is a little bit bigger, right? And if I take a look at this thing, so I might as well so I want to find the distance between them. So what's the distance between this value and this value? 32. It's single integer. It's a single integer. So is it like wasting a little bit of memory on a heap? It could be just wasting a little. It could be just allocating like 4 bytes or something. I'm super goddamn curious, actually. Is there like any source code? Like, how can we even take a look at the implementation of malloc? It's really interesting. So we need to find the source code of GCC, but even within the source code of GCC, it could be kind of difficult to find. GCC source code. All right. So there's a GitHub mirror in here, and if I take a look at the malloc, so I'm really curious, like, what do they do? So there is malloc mac or something. There's a testing. Okay, there's a lot of stuff in here. Maybe we could clone that stuff super quick. I hope I'm not going to a very huge rabbit hole just to quickly check out the implementation of this thing. So I'm pretty sure the history has a lot of commits, so I probably need to do shallow copy or something. Shallow copy. I forgot how. Shallow clone. I think it's called shallow clone. How to use git shallow clone to improve performance. Huge article on like 100 screens, and it's a single command actually. I remember that it's basically depth. I mean, come on, it's a depth. Yes, it's a depth argument. Yeah, so remove this entire article and just replace it with a single like depth thingy, and that's it. You don't need to write too much about it. Come on, people, come on. Okay, so this is gonna be something like this, and let's do a shallow copy, and it didn't work. The fuck? And it, what? A non-ASCII option in string. Are you fucking kidding me? Is it because, oh, can you spot the difference? Freaking, like, you're not only like wasting my time with your huge article, you also made code in your article not copy-pastable. My god. Okay, I'm super mad, like holy fucking shit. So let me wait. It's perforce. Really, perforce. Perforce is like another like version control system or something. I'm so disappointed in you. Are they doing that intentionally? I have no idea if they're doing that intentionally, and I don't care, to be fair. My god, my cat, oh my god. Okay, so shallow copy works fine, I suppose. I don't remember what shallow copy does. It just doesn't clone the whole history, I suppose. Okay, it's fine. So the first thing we can try to do, we can try to find any files that have something related to malloc in them, and we have shit ton of them. Okay. So what can we have? These are primarily like test suites. So fix includes libliberty, libgo, analyzer, sm alloc, config, malloc allocator, libffi, libgcc, nvptx, malloc. So I don't even know what to look at, right? Because config's probably not in the config. Experimental allocator, mallocator. Yes, I'm not the only one who came up with that idea. DL malloc. I don't know. It's not obvious where to look for the malloc implementation. It could be not in the GCC. It could be in, yeah, it could be actually in glibc. GitHub. An official mirror. Oh, look at that. Google is useful, question mark? Excuse me? Google Google gave me a relevant result. The fuck? Okay, not bad at all. All right, so can we take a look at the malloc? Okay, so there's some hooks or whatnot. Arena.c, support for multiple arenas. So do you have like H? If I take a look at the H, and if I take a look at the malloc. So is malloc in fact, no, it is not in fact a macro. For a second I thought maybe it's a macro. So yeah, here it is. This is what I'm looking for. If I take a look at C, is it located anywhere here? Doesn't seem to be located anywhere here, but we're still loading the page. Okay, so it's quite funny that there's like no, you don't have an actual implementation in here. Sysmalloc, so there is a sysmalloc. Routines dealing with the system allocation. Okay. libc malloc. Okay, maybe that's what it is. Yes, libc malloc. It's probably that's what we need in here. Okay. So here's the bytes, right? So you're trying to allocate the bytes and check requested size. Okay, so you checked requested size. And then maybe it is in fact in so it's probably buried deep down somewhere in like check requested size or something. I don't know. Yeah, but I would assume it's just like wastes a little bit of memory. So it uses int alloc victim. Nice one. Okay, so I'm wasting my time at this point, so whatever. Whatever. I was just a little bit curious. Probably should have not gone that, but yeah. So okay, our implementation right now. What does it do? So we have yeah, we can now free chunks and we can allocate chunks and stuff like that. But what's interesting is that even though we like free the chunks, they're not reused whatsoever, right? They're not reused because we're essentially like appending the new memory. We're just appending the new memory to the heap. So to start reusing the memory, I think we need to get rid of the notion of heap size. Yes. I think we need to get rid of the notion of heap size. We're not going to have a heap size anymore, and we're going to have, at the beginning of this entire stuff, we're going to have a single free chunk. That chunk is going to start at heap, and the size of that chunk is going to be heap cap. Yeah, maybe I could also do something like size of heap. There we go. So essentially, if you are trying to allocate something, you need to iterate through all of the chunks, right? You need to iterate through all of the chunks, find the one that fits the best in your case, and just allocate everything there. And again, so if the chunk doesn't fit perfectly, you would have to split that chunk into two. So you have big chunk, you allocate a little bit of memory within big chunk, that goes into the allocated one, and the rest goes into the free one. So that's how it's gonna go, I suppose, I think. So, all right, so if I try to do something like this, is it gonna work? Is it gonna work now? Yo, braces, something, something, something. Scalar initializer. This is not a scalar initializer. Oh, yeah, I know what you're talking about. So because of that, the count, yeah, we have to set, first of all, count to 1, right? And then we're gonna have chunks, right? And within the chunks, the first element is gonna be equal to that, and I can even do something like 0 equals. So I'm specifically indicating that right, that you have something in here. All right, and now if I try to recompile, everything seems to be okay, and it doesn't compile because you don't have a heap size anymore. All right, that is fine. So, and the first thing we probably want to do, right, we probably don't even need to check any of this shit, right? So we actually removed the notion of heap size completely. So what you do now, you're iterating through the free chunks and find the one that fits perfectly for you, right? So it's going to be I less than freed chunks, it's going to be count plus 1, and if freed chunks chunks I size is greater or equal than size. So keep in mind that they're sorted in ascending order. So first come the smallest one and then the bigger one. So as soon as you find this one, you found the perfect one. So don't even worry about that. So we need to take that chunk and we need to remove that chunk from the freed chunks. So this is going to be something like chunk. So we're going to be basically copying it here, and free chunk list remove freed chunks, and I'm removing ith chunk. Cool. I'm removing ith chunk. So then what I want to do, so the final result that we're going to return in here is going to be obviously equal to the start of the chunk. So this is going to be the final thing that I'm going to be removing here. Then I want to insert allocated chunk, right? I want to insert allocated chunk. So that means I'm going to do chunk list insert alloced chunk. And it starts at chunk start, but the size of that chunk is the user size in here. There we go. So this thing is allocated now. And now I need to check if, yeah, so we need to know the size of the tail, right? So we need to know the size of the tail. So here is the chunk. So the size is that. And we need to do something like tail size, right? So to know the tail size, I'm taking the size of the chunk and subtracting the user size. This will never be negative. It will never underflow because both of them are sizes. So it will never underflow because we're checking this condition, right? So this size is always greater or equal than this size. So that means this entire value is going to be 0 or greater than 0. You don't have to worry about that. Furthermore, maybe it would make sense to actually replace this entire thing like this, so it's a little bit more obvious what exactly we're doing in here. So on top of that, we might as well make it const because I don't plan to modify it anywhere. So yeah, so everything is checked in here. So here's the tail size. I don't plan to modify that thing. I don't plan to modify that thing either. So here's the tail size, and we're appending a new chunk in here. And if tail size is greater than 0, we have a little bit of a free chunk that we need to push back into the list of free chunks. So it's going to be chunk list, remove, and actually not remove, insert freed chunks, and we're inserting. This one is interesting. Chunk start plus size, and the actual size is tail size. There we go. So this makes sense to actually have it like that, because at any point I can just return chunk start in here. So PTR is not existing concept in this particular case. Okay, and after this condition, right, you instantly exit, and if you reach the end of the loop, that means you couldn't find any free chunk that could fit your memory allocation, and we're gonna just return out of memory, right? So there you go, it's out of memory. Yeah, that's basically it. That's basically it. So we can just basically comment it out and just print everything without any allocations. And as you can see, allocated chunks is that, and we have a single free chunk of the size of 640 kilobytes. 640 kilobytes. All right, so if we allocate this kind of stuff, let's see if it's going to even work. Okay, that's very interesting. So we have a bunch of allocated chunks in here. All right, a bunch of allocated. And then we have a bunch of free chunks in here. And we have a huge chunk here, right? So this is like the rest of the heap, and everything looks fine. Also, we have a size 0. Oh shit, right, so we forgot to check the case when you try to allocate you know, size 0, right? If size greater than 0, right? If size greater than 0, blah blah blah. So that should never be a thing, right? That should never be a thing. So we get that, but what's interesting is that now if after all of this stuff I will try to allocate 1, 2, 3 up until 4, right? I hope that these chunks will be taken instead of like chopping off like another huge one in here. Well, we can also check the following thing. We're gonna allocate like 420, and let's see what's gonna happen. Yeah, there we go. So here is a 420. So we chopped off a little bit off of that. So everything seems to be okie dokie karaoke. And what if I try to... So as you can see, trying to allocate that didn't actually take any of these chunks, right? We had allocated the size that is bigger than any of these things. So the heap is sort of fragmented. And if I try to allocate them yet again, like this, they in turn will be taken. Okay, so everything was taken correctly, more or less. All right, that's very interesting. That's very interesting, but consequent chunks are not really like merged together, if you know what I'm talking about. That would be kind of cool if we had a special way to merge chunks together somehow. So maybe we could have a special function. We know for a fact that the chunks are sorted by a pointer. So if you have two continuous chunks, you can easily identify them. Essentially, the previous chunk pointer plus size should be equal to the pointer of the next chunk. And if something like that happens, you can easily merge these two chunks together. So you don't even have to worry about this kind of stuff. So yeah, what would be the easiest way to actually do that? So can I do that in place? Can I do that in place of the chunk? Because, all right, so imagine that I have something like this, right? So here are the chunks, and I'm iterating them by pairs, and then I like determine that these two are like connected. So that means I sort of merge this one into that one, and now you have a hole in here that you have to fill with something, right? So that means you need to move this entire stuff to here, which is not particularly convenient, not gonna lie. So one of the things we can do instead is actually have this third like temporary chunk, and essentially as you iterate through these chunks, and you did remind that some of them can be merged, you actually append them to the new list, and then you replace the previous list or something like that. So that could be done with linear time instead of quadratic time. So and so what's interesting is that the capacity of the lists is not really that big, so maybe the entire list could be quite easily copied because it's just a metadata, right? It's just a metadata. So maybe we need to have some sort of function chunk list merge. Yeah, let's call it merge. We're gonna accept the pointer to chunk list that you're trying to, merge and stuff. And I wonder how we're going to be approaching this entire stuff, right? So we need a third one, and where we're going to be allocating the third one? So maybe we could pass a temporary one, something like this. So it's going to be TMP, and we're going to be iterating the chunks of that list and copying the merged versions into that one. So yeah, that could be actually quite easy. And then you can try to copy him back or reassign back, and they should be reassignable because, as you can see, there's no pointers in here. It's just an arrays and stuff. So yeah, let's give it a try. So it's going to be size ti less than 0. Oh yeah, so the problem that I'm trying to solve that, if you actually deallocate every allocation, right, you're gonna end up with fragmented, like with this situation, right? So you essentially lost all of these chunks if you're always gonna do bigger allocations, because the allocation is gonna be happening in these specific chunks. So all of these chunks need to be merged together, right? They need to be merged together. Otherwise, like the next allocation, like heap free 1000, right? So, and it's like, it's not gonna even use any of this stuff, right? So heap alloc, right? So yeah, there we go. So it didn't use any of these things. So this entire stuff is completely lost. Even if you try to do 10, I think, yeah, I think it won't even allocate 10 in any of these chunks because there's just no big enough chunk, even though if you merge all of them together, you're gonna have enough memory for this kind of stuff. So yeah, that's what I'm trying to solve in here. I want to have a routine that merges the chunks somehow. All right, so let's iterate this entire stuff. So it's going to be 0 less than list, and so maybe like linear iteration is not particularly good way to go, but maybe it is. So because first you want to do what? You want to push a thing into that one, and as you go, yeah. So first of all, you also want to clean this chunk like this. So basically, if you put this TMP, all of your data in TMP is automatically lost. So you have to be aware of that. Okay, now if I do size I less than list, oh, and this one could be actually const because it's not going to be modified, right? Because we're merging into a different one. Size plus I. All right. If TMP count, this is actually called count, is greater than 0, we do have a top, right? So this is to do for now. Otherwise, if it's equal to 0, what we essentially can do, we can push the current element chunk C on top of the on top of the temporary one. So it's going to be something like TMP count plus plus equal this. So will this ever overflow? That's a good question. Will this ever overflow? Or maybe it would be actually better to use like something like insert. But insert is actually linear. But if you're inserting things in a sorted order, I think it's always going to be constant, right? So if you're inserting things in a sorted order, it's always going to be constant. And on top of that, you have a check of overflow in here. So maybe it does make sense to do it like that. All right, so this is going to be chunk. This one is probably going to be constant because I don't plan to modify it anywhere. List chunk I, right? So this is the chunk I. If this entire thing is empty, we're going to be doing something like chunk list insert. We insert in TMP, we're actually inserting chunk start and chunk size. There we go. So we inserted this entire thing in here. If this thing is like has something on top, we want to check if it's mergeable with the current chunk in here, right? So TMP chunks TMP count -1. We need to take the pointer, right? So let's actually call something like top chunk, maybe. Yeah. So, but this one has to be actually pointed top chunk. Yeah, something like this. So we've got a top chunk. So if the top chunk start plus top chunk size is somehow equal to the chunk start, right, to the next chunk, that means these two things could be easily merged. I think this is my logic. And how can you merge them? Well, you just add the size of the previous chunk of the next chunk to that one. There we go. So you effectively merge them. Otherwise, you are inserting that chunk in here. You're inserting that chunk in here. This is very interesting. So there is like duplication in here, and I wonder how you can prevent that duplication. So it would be cool to have a special operation, but I'm not sure if it's easy to do. So to be fair, I want to keep it like that because it's a very straightforward logic here. So in trying to compress this logic will make the code very, very unreadable in my opinion. So we keep merging these things and yeah. So the next chunk, if you don't have anything on top, you just push it there. If you have something on top, you store the pointer and you check if the start plus count equal exactly to the start of the next chunk. You basically add the size of that chunk to the top chunk and you ignore everything else, right? Otherwise, if it's not equal to that, you just append that chunk there and it becomes the new top chunk, essentially. So, yep. And chunk list insert is in fact O of 1 if you inserting the elements in a certain order, right? So it's only going to be like in worst case if you try to put like a very small number in there. But in this particular case, it's not going to result in O of n. It's always going to be O of 1. So there are guarantees for that. All right, so we have a way to merge these things, but you only merge them into a different one. So list in that case is more of a like SRC, and this is like a DST, right? And in the spirit of Intel assembly, the destination has to be the first argument and source has to be the second one because you're moving from right to left. All right, so let's actually try to compile that, and here instead of TMP you have DST, right? So there we go. Save. Yeah, it's save. And has no member set. Okay, this is because it's a count. Anything else? And instead of list, you have SRC. Boom, boom, boom. Nah. not that list, excuse me. Anything else? src chunk s. Okay, cool. So let me see, chunk list. Implicit declaration. Okay, so that means we have to take chunk list and essentially maybe move it up a little bit, like above the chunk list merge. All right, okay, so now when we essentially start the allocation, so when we free the things, maybe it doesn't make any sense to merge them. So I'm just thinking, what's going to be the best way to actually like compress everything? When's going to be a good way to compress everything? Maybe when you try to allocate something, right? So you try to allocate something for the first time, and yeah. Well, another interesting thing could be is that if you ran out of memory completely, right? If you like after a first allocation you cannot do anything, maybe only then try to merge those things and try again. You see what I mean? And try again, because this operation is quite expensive, right? You need to iterate through all of these things and stuff like that, but maybe it's not that expensive because it's linear and whatnot. I don't know, we can merge them maybe after each allocation, right? Maybe after each allocation. So here you have like a free chunks, and maybe you can have additional like list of chunks for the temporary, like temporary chunks, right? Something like this and all of that. Of course, let's Emacs, what are you doing? What are you doing? What are you doing? So, and yeah. Okay, so you're trying to allocate something, and what we're doing here is a chunk list merge, right? So this is going to be merge, and we're merging them into TMP chunks, right? We're merging all of that into TMP chunks from freed chunks, right? So, and then we are assigning TMP chunks back into the freed one. So I wonder if it's gonna work or not. Look at that! It worked! So, look. So if I remove this thing, it did 10 allocations, and you try to allocate 10 bytes, and it allocated it like somewhere here, and it was never actually merged back. But if I do that, I will try to merge them yet again, and yeah, everything was merged appropriately. What's interesting is that if you fragment your heap too much, right, something like this, it can be equal to 0, right. I don't think it's gonna work. Yeah, to be fair. That is sus. That is in fact sus. How did that work? It feels a little bit sus. Because it's 1. Is that because I would expect this thing to be fragmented, but maybe it's not fragmented because we have one allocation that doesn't. Yeah, so there was one allocation that didn't do any allocation, and because of that, it like created a chain that is not like that was easy to compress, I suppose. Right. Right. So now everything looks more or less correct. And this entire stuff is not particularly compressible. Or is it? If you have this kind of thing, it should not be compressible. So 0, because if you add 1 to this, it's gonna work. I don't know why it didn't work. But yeah, what if I do like a couple of more of these things? I don't know. All right, so I don't quite understand why. So this should be compressed, shouldn't it? So because if you take a look at that, yeah, and if you take this part and add 1, it's going to be equal to this thing, but it did not get compressed at all. So free chunks, and I understand. Oh, it's still because I disabled it. All right. But the question is, why does it get compressed? I don't understand. Oh, maybe because now it creates a very complicated process. Ooh, okay. The process could be actually pretty complicated now, because you allocate and then deallocate the next one, and because of that, that got merged. All right. Okay. So let's actually take a look at what's going on. This is very interesting. I want to get down to that because it's quite important. Right. So what we're doing, we're allocating 1, 2, 3, 4, 5, and so on bytes, but we're also deallocating each even one, right? So each even one gets deallocated. Okay, so if we do something like this, so right. So first 1 allocation, then 2, and then instant deallocation, which results in this chunk getting merged back into the big one. So then we allocate 3, and then we allocate 4, and instantly deallocate, which results in that. Okay, so because of merging the chunks now, like, you cannot easily fragment that thing. You cannot easily fragment it. Yeah, all right, so that's very interesting. We can try to fragment it somehow if we allocate array of pointers, right? So let's actually put n into here and allocate array of some pointers. So it's going to be ptrs n, and let's also zero initialize this entire stuff. So this one is going to be something like less than n. I also want to actually try to allocate like a 0 or whatnot. So ptrs I, we're allocated this entire thing. So we just keep allocating them, right? So, and we keep storing them. So here are all of the allocations and all of the free chunks. And now I'm going to iterate this one more time. And, right, if I is divisible by 2, right, we're going to deallocate that. And hopefully that will fragment the heap. Right, hopefully that will fragment the heap. Okay, and let me see. Yeah, okay. So if I don't deallocate them, 1, 2, 3, and deallocate them. This actually should. Am I an idiot? Like, why are they not compressed? Why are they not compressed? Yeah, and they should get compressed or something. Yeah, they got compressed, and as you can see, they got allocated at the beginning here. Wait a freaking second. Like, why? Why this works like this? Because it shouldn't, right? Shouldn't it? Right, it's gonna be 1. Because I'm allocated 1, 2, 3, right? 1, 2, 3, and then if I deallocate this entire thing, there should be a fragment. And then the fourth one, yeah, everything should be fragmented as hell. So something doesn't work properly. Something definitely doesn't work properly. So, yeah. Let me quickly find out. Okay, I think I found it. It's really, really dumb. So it's in heap 3. So yeah, the free doesn't work correctly. So essentially, you try to find the pointer in allocated chunks, but how are you sure that it's the right one? So if you assert, right, pointer should be equal to alloced chunks index start, right? So that assertion should be correct, but it is not. So yeah, binary search, by the way, binary search. To be fair, this goddamn binary search could have been implemented linearly way simpler, right? So it could be something like size t less than least count, right? And essentially if least chunks chunks I start equal ptr, just return I, otherwise return -1, and of course you want this thing to be integer. And yeah, so it's probably something with comparison or something like that. So okay, let's actually do list find linearly. I don't think it's going to be that bad. All right, so this thing is I know that it's never going to be less than 1 in this particular case, so I can quite easily just return that. But maybe because of that, you want to make this thing size t and convert it to integer only if it is like that. Okay, so all right, now it is in fact fragmented properly. Right, and if I try to allocate something in here, yeah, it's gonna allocate in the next one, and none of these things are gonna be merged together anyway. So it was because of the binary search, but because we got rid of the binary search, it's gonna be a little bit slower. But I think that's basically the idea behind memory allocation, right? So you basically keep track of the chunks, and the only speed improvement that you can come up with, that I see you can come up with, is basically improving the separations, right? So you want to improve the insertion into the list of chunks, removing from the list of chunks, merging the list of chunks, and so on and so forth. But I think maybe that's how usually you know, memory allocators implemented. I don't know. So this is like the algorithm that I managed to come up with myself. It's a pretty crappy allocator, but at least I learned something. That was actually fun. So unfortunately I ran out of time, so I also wanted to implement the garbage collection. But maybe we're gonna do that next time. So maybe we're gonna dedicate that to the next stream. Right. All right. Yeah, and there's a lot of things we can do in here. We can try to improve the performance of all of these operations because all of that is linear. But all of that is going to be next time. All right. I'm going to put that in the GitHub, and I'm going to put the link to this project in the description. Thanks everyone for watching. Hope it was interesting. It was definitely interesting for me. I learned a lot of things. So see you all tomorrow, as usual. See you all tomorrow. Thanks everyone. I love you all. Mwah.